All right, hello everybody. We're getting to the end of this problem set, which is quite nice. I think this is the longest problem set because it's the one that I wrote, and amateurs always overdo it. Yes, okay, so we're asked now to change our setup. We're still in the quadratic land. You see that the bank still has this quadratic K target. And now the bank is not allowed to directly choose pi, and instead they have to have an instrument, which is change in the money supply. But the instrument isn't perfect. So they're going to try to move pi by delta m. They choose maybe delta m equals 1. They want pi equals 1. But what they really get is delta m plus random noise with sigma nu. So they want to move it by 1, but they only move it by 0.8. And they don't know what that noise is going to be. Okay, so what we should find is that the answers are largely similar to those that we saw in the previous answer, or in the previous question, question 3, but there's going to be some additional noise parameters. And we should expect noise here. There should be like a nu. We should expect that the noise should not change, no change, maybe, because it's in expectation, right? So if there's additional noise here, maybe there's no change in the households problem. And here we should expect that sigma nu shows up. Okay, because it's quadratic, so we get variance terms, and the variance of nu is sigma nu squared. So we should expect a priori that sigma squared nu is going to play some kind of role. It's going to look similar to what we got in the first time. It'll be like, some coefficients, let's call it some coefficient alpha times yn minus k squared plus some coefficient beta times sigma squared epsilon, and then maybe some coefficient delta times sigma squared nu. Like, this is the form of the social loss function that we're expecting. Some baseline that they can't possibly avoid, plus some noise that results from the shocks to the economy, and then some noise that results from the imperfection of the central bank. The central bank's imperfect ability to control the target pi. Okay, so that's just sort of like our expectations. It's good to form these expectations because it gives you intuition about whether or not the answers you're getting are correct. So let's do it. Let's do the central bank's problem. We're going to take the utility. We're going to minimize negative UCB with respect to delta m and y, subject to this and this. And we see that we can substitute away pi and y and just choose delta m. Okay, so let's make that substitution. We're going to have that the negative UCB is minus 1/2 lambda. Y is yn plus a, and we know what is pi. Pi is delta m plus nu minus expected pi, close parentheses, plus epsilon, close parentheses, squared, minus 1/2 delta m plus nu squared. And so this is a function of delta m only. And so now we can minimize it with respect to delta m, which is the choice variable now. Set it equal to 0 to get the FOC. Minus 1/2 carries along. The 2 will come down and cancel the minus 1/2. So really just minus lambda comes along. We get the inside, yn plus a delta m plus nu minus expected inflation plus epsilon. Derivative of the inside is just a, because we have a delta m here, so I'll just add it out front. I left a little space. Over here, we're going to have the 2 come down and cancel with the derivative of the outside, so we're just going to get minus delta m plus nu, and the derivative of the inside is just 1. So we're done. So we set this equal to 0. And we need to pull out the delta m's and bring them to the other side. So there's a delta m here. It's going to be a squared lambda delta m. So we get a squared lambda delta m. And then here we just have plus delta m. I've moved these to I've added them to both sides because this is negative, this is negative. That's equal to minus a lambda yn plus a nu minus expected pi plus epsilon minus nu. Yes, looks right. Factor out on this side, so we get 1 plus a squared delta m. This is all looking very similar. This 1 plus a squared lambda appeared over and over and over again when we did the other one. And then we're going to have, I'm going to push this minus sign into the parenthesis. So we'll get a lambda, and then I'm going to flip everything. I'm going to flip everything. I'm missing a k. I'm missing a k. You guys got to tell me that. I apologize. Let me change color so it's clear where the error is. The error is here. There should be minus k. And here there should be minus k. So when I flip things around, we're going to get k minus yn minus epsilon minus a times nu minus expected lambda. Close parentheses, minus nu. And the only other thing I'm going to do is so that things match what we had in the other case. So first we can divide through. So we're going to divide both sides by 1 plus a squared lambda. So we're going to get a lambda divided by 1 plus a squared lambda. I'm going to push this minus sign into these parentheses to turn that around so that it matches what we had before. So we're going to have k plus a times expected inflation minus nu. So you see I just flipped that around and pushed in the thing, and then we're going to subtract yn, and then subtract epsilon, and then subtract nu over 1 plus a squared lambda. And there is our optimum, the optimum choice for the money supply. It asks for the optimum level of inflation. The optimum money supply implies an optimum level of inflation because pi star will just be equal to optimum inflation, or optimum change in money supply plus nu. So we know what is the optimum change in the money supply. It's a lambda over 1 plus a squared lambda, k plus a expected inflation, minus instrument noise, minus natural rate, minus productivity shock, minus, let's do plus nu minus 1 over 1 plus a squared lambda nu. And we can see we can make a simplification here. This can be written as plus 1 plus a squared lambda minus 1 divided by 1 plus a squared lambda. I just wrote 1 as 1 over a squared lambda. 1 plus a squared lambda over 1 plus a squared lambda. We can imagine that that goes right here, right? So there's a 1 here. I just wrote it as 1 plus a squared lambda over 1 plus a squared lambda, like that, times nu. Right. So now that we've rewritten this, we can make a simplification. Well, let's rewrite the whole thing. Let's not go too fast. So we get a lambda over 1 plus a squared lambda, k plus a times expected inflation minus nu minus yn minus epsilon, close parenthesis, plus, and then what's left here, I'm going to write this aside to match this coefficient. So let's write this as a lambda over 1 plus a squared lambda a nu. Yep. Because what that means is that I can bring this inside. And we see that we actually have a epsilon pi minus a nu, and then we're bringing in a nu, so it cancels out. So what we're going to get is that, let's come up here because my head is somewhere down there. We have a lambda over 1 plus a squared lambda times k plus a expected pi minus a nu plus a nu minus yn minus epsilon. So these two cancel, and we just get that a lambda over 1 plus a squared lambda times k plus a expected pi minus yn minus epsilon is pi star. Head check a little bit. I'll pull it down just a touch. There it goes. Okay, so now you can see that actually we get the exact same answer as the no noise case. And this should kind of make a bit of sense because the bank can't do anything about that noise. And the noise is centered at 0. So the bank's absolute best guess about what will happen if they choose any level of delta m is that they will get that level of delta m. So in their decision-making process, they just totally ignore it. So our expectation was wrong. I said that I expected that some nu would show up, and in fact, nu does not show up in the pi star. Nu does show up in the delta m. Okay, when the bank chooses delta m, they do take into account this nu in two places. So maybe maybe the intuition is something like this: the bank chooses delta m, taking into account this potential shock, but they take it into account in such a way that when they compute the target pi that this delta m implies, that target pi will be precisely equal to what they want without any adjustment. So stated another way, we can reason backwards. The bank first chooses a pi star that it wants, and then it knows that it can't perfectly get that pi star. It's going to get that pi star plus a bit of noise. So when it chooses a delta m to meet the pi star that it chose, it will take into account that noise here and here. Okay, but for the optimum level of inflation for the economy, precisely the same, no change, which is a nice little result. So in the next part, we will do the household, and we expect the household won't change either, but we'll see. And we still expect that we'll see some variance terms of the instrument pop up in part C, but we'll test that theory as well. So I'll see you there. All right, hello everybody. I spent some time thinking about this question after I finished it, and it's not sitting well with me because the answer for pi star is precisely equal to the answer we got in question 3 without this new control variable noise. And so I hope you can see that the answer to the household problem will be exactly the same because, yeah, they choose expected pi equals pi star, and then you'll do the same exact rearrangement and get the same answer. And then, as a result, the answer for part C, the social utility, will be exactly the same. Because, yeah, pi is exactly the same, expected pi is exactly the same. You plug it all in, you get the same answer. So there will be no sigma squared nu that shows up. Yeah, and I want to know why. So we go to the textbook here in Walsh 7.2.3, and we see this is the optimization for the bank. So there's a timing difference. We have to pay attention here. It says the central bank is assumed to act before observing the disturbance V, or nu. Oh, excuse me, this is the linear case. I apologize. Let me scroll down to the quadratic loss with K. Here's the answer. Here. Okay, so delta M is chosen after observing supply shock E, but before observing the velocity shock nu, what I call the instrument noise. So we have to pay attention to the information set, and we have to take an expectation on delta M. So you can see that their delta m here does not contain a nu. Okay, I really don't like this, but let's go over carefully how their problem is set up. And this has to do, again, with information. Okay, so in class, someone brought up Settlers of Catan, which is a nice, thinking about a game. But, any board game, any game with a dice will do. So your turn begins. Okay, you are the central bank. Your turn begins. You will roll a dice. You will roll a dice. And the dice will give you epsilon. Okay? So turn begins. You observe epsilon. Now it's decision time. This is start. Now it's decision time. You need to choose delta m. Okay? After you choose delta m, you will roll another dice, which will determine, and this is going to give you nu. So this will determine pi given your delta m. It's not clear at all. Given your delta m and nu. Okay? And then the households choose. Then the households choose expected pi star. I guess expected pi. Okay. So this is the important point, is that when we solve, epsilon is known. So epsilon stays inside of our equation. Epsilon is fine, we know what this is, but we don't know what nu is. So in our delta m equation, this is a random variable. Okay, so we need to take expectation of m. We need to take the expected value of delta m, given that epsilon is known. Okay, and that will be delta m star. So you're averaging over every possible outcome on this dice. You're saying, well, I don't know what that dice is going to be, so I need to make the best choice I can for whatever the case may be. That's what an expected value means. And so from this blue box, I hope you can see everything is additive. There's nothing that's multiplying together. So the expected value can just go on everything. The expected value of k is k. The expected value of pi is the expected value of pi. The expected value of nu is 0. The expected value of yn is yn. The expected value of epsilon, in this case, is epsilon, because we're conditioning on the value of epsilon. That's an important point. This is why all this information set stuff, authors, papers often bury this inside of their assumptions, and you have to be super careful. You see, I didn't understand this is what their setup was, and so I got a totally different answer. Okay, so but if we condition on, we know epsilon but we don't know nu, then nu is 0 in expectation, yn is yn in expectation, epsilon is epsilon in expectation because we already observed it, and this term is 0. So what we get is alpha lambda over 1 plus a squared lambda, I think it's an alpha, k plus a expected pi. The nu is 0 minus epsilon minus yn. Okay, and now this is delta m star. This is our best guess, given what we know about the distribution, given what we know about this dice, and given that we already saw this dice. And now, when we compute pi star, we'll add the noise. So here we determine pi star, right? After we choose mm, and now we choose pi star, and we add on the nu. So we get delta m star plus nu. Okay, so we'll have just this. So then pi star, that will be equal to this, plus nu. And now you see that the nu carries through into the problem, and The household problem will be slightly different. We'll have the plus new in the household. Maybe not. Maybe it'll drop away in expectation. I'm not sure. We'll do it. But definitely, when we plug in pi star into the social utility, the new will be there. And so we have the possibility to get some variance from new showing up in the utility function, which is what we expected. Okay, so this information game setup, whenever you're solving one of these models with expectations and random variables, be very careful about who knows what when. Okay, and if you don't know that, you need to email the authors or something, because this is so important. And you see that changing the assumptions about it changes everything. You see the way that I solved it up here, I'm assuming that we rolled 2 dice in the beginning, right? The turn starts, I observe 1 dice to roll epsilon, I roll another dice for nu, right? And then that gives you this equation. If you roll 2 dice in the beginning, you get this equation. If you roll only 1 dice, and then you choose, and then you roll another dice for the nu, you get a totally different answer. So I hope that was clear. The correct answer, we're going to go with the book. So the correct answer is this here. Delta m star is going to be equal to the old pi star, but then we're going to add in the new. Okay, cool. I will see you in the next video.